All right, in this video, I'm going to cover section 3.1, probability distribution and probability mass functions. So, chapter 3, we're going to study discrete probability distribution with discrete random variables. Okay, so what's the probability distribution? Probability distribution is a table or a graph showing the probability for each possible random variables, value of random variables. Okay, so for example, so we learned about the function, right? F of x. We learned about a lot of different type of functions in calculus, right? So now you may just consider that you can consider that these functions now represent the probability functions. So input is the random the value of random variables. The output is a probability in this statistic course. Okay, so now let's see probability distribution and probability mass function. So this we learned about discrete random variable, right? There are two types of random variable: the continuous random variable and discrete random variable, right? So discrete random variable is countable, right? So keep in mind this. And then now see example 3.1 flash recharge time. So the time the time to the recharge the flash is tested in three cell phone cameras. So here's a table right there. Okay, the probability that a camera meet the recharge specification is zero 0.8, and then the cameras perform the independently. We have seen this one. Oh no, never mind. Yeah, so this 3 point right there. For the sample space for the experiment and the associate probabilities, that's right here, table 3.1. See three camera right there, and then you show the pass and fail for that recharge specification. Okay, and then probability is a 0.512. First one, all the three camera pass. The probability the three camera pass is the 0.512. Okay, in this case, random variable is value of random variable 3. You see that here? Now what? So if pass, fail, for each camera, we have two outcomes, right? Pass or fail. So that categorical values converted to the random variable, actually in natural number 0, 1, or 2 or 3. So now that's the exact, this is really good, one of the basic example of random variable. What's the random variable? A function from the outcomes to the what? Real number. Okay, so now the problem is this. See, for example, because the camera are independent, and the probability that the first and second camera pass the test and third one fail denoted as PPF. Keep in mind all the probability that you know, I mean, three events, camera one, two, three events are what independent, right? So we don't have to consider the conditional probability. So probability that first two camera pass and then the third camera fail gonna be zero 0.8 times zero 0.8 times zero 0.2, which is 0.128. Okay. So now then that's a really a simple example. Okay. So when you find the probability, then you just look at the let's see, yeah, we just look at the table, right? And then um the just figure out the probability for each camera. Okay, so then multiply them, right? But what if we just the outcome, I mean, just we got to complicate the tables with a lot of numbers and I mean outcomes here. So then the problem give you a function of the probability. Then we use that function to figure out the probability for each uh, random variables. Okay, for this one, 0.2128, 0.1, that's the actually what probability that x random variable x equals what 2, right? You see that here for each random value of random variable 2 here, the probability is the same 0.2128, 0.2128, and then 0.2. You see that here? Okay, let's see. So, and then what if then the probability that what x equals 1, probability x equals 1 means that two cameras fail and the one camera is a pass. It's going to be 0.2 times 0.2 times 0.8, which is a 0.032. You see it here, 0.0 here. Okay. So for each random variable, each probability is unique, right? You can see. Okay. So now then we can construct the or define a function mapping from random variable to the probability. That's the probability um, function. Okay, but specifically, if the type of random variable is a discrete, we say that the not just probability function, but probability mass function right there, probability mass function. Okay, so now example 3 point. Let me skip example 3.2. Okay, just look at it by yourself. Okay, let's see example 3.3. There is a channel that is a bit transmitted through a digital transmission. Channel is received in error. Let x equal the number of bits in error in the next 4 bits transmitted, and the possible values of x are 0, 1, 2, 3, 4. Based on a model for the errors that is presented in the following section, probability for these values will be determined. And suppose that the probabilities are these, okay, here. Okay, so now then the probability. See that now you can see that, oh, then random variable must be this is we're dealing with a discrete random variable, right? 0, 1, 2, 3, 4. Okay, so now the probability distribution of x is specified by possible values along with the probability of each. Yeah, so yeah, this is a probability distribution. I told you what's a probability distribution is a table or graph, or just a kind of something visualize data was visualized, okay, with what random variable, okay. So now a graphical description of probability distribution of x is shown here. Okay, so for each, the x-axis represents discrete random variable values of random variable, okay, 0, 1, 2, 3, 4, and then for equal axis represent probability. So now here f of x represents what? Probability mass function. Okay. So it means that f of 0 is 0.6561, f of 1 is 0.2916, and the f of 2 is 0.0486. Okay. So now for discrete random variable x with the possible values x1 through xn, okay, here we assume that there are finite number of discrete, I mean, discrete values of random variable. Okay, so now then that possible probability mass function should satisfy these 3 conditions. Okay, so when you sometimes you may get the problem asking you to show that that function is a probability mass function, that you have to show that that function satisfies these 3 conditions. Okay, so f of xi must be greater than or equal to 0. Makes sense. I told you every single probability must be what? Between 0 and 1. Okay, so now the sum of all the probability must be equal to 1. And then f of xi must be equal to what? Probability that random variable x equals xi. So this is probability. The right hand side is what? Actually p of xi. Okay, so that f of xi actually you have to show that that function value actually represent, I mean, equal to probability of xi. Okay, but um most of cases, most of problems, you have to show second, okay, at first and second, okay. So you don't have to mm, specifically show this one. I mean, yeah, technically, yeah, mm, you barely, have to show this one, the last one, okay. Okay. So now example 3.4, wafer the wafer contamination. So let the random variable x denote the number of semiconductors wafer that need to be analyzed in order to detect a large particle of contamination. So assume that the probability that a wafer contains a large particle is 0.01. Okay, probability that the wafer contains a large particle is 0.01, and that the wafer are independent. Okay, so it means that what? So when you just check the first, analyze the first wafer, okay, and then that is not that doesn't affect the probability the second wafer contains a large particle contamination. Okay, so it's independent. Determine the probability distribution of x. Okay, so now then let me see. First one, let me follow the all the letters what they use. Okay, let P denote the wafer in which the large particle is present. Okay, let A denote the wafer in which is it is absent. Okay, so the sample space of the experiment is infinite, and it can be represented as all possible sequences that start with a string of A and end up with P. So P, AP, AAP, AAP, something like this. Okay. So first here. So the possibly we may get the what large particle contamination in the first trial, right? Or we may get the second trial. We may get that contamination second trial or third trials, and so on. Okay, so let's see. Okay, so now then yeah, you may say that. Okay, so what if we got the wafer contains large particle contamination in second trial and also third trial. Yeah, you can say that, but I think here in this example, the sample space is defined by the I mean that experiment. We find the wafer containing large particle, we stop. Then we stop. Okay. So now then consider a few special cases. Okay. P of x equals 1 is P of p equals 0.01. Why? You see that? Probability the wafer contains a large particle is a 0.01. That's why P of p equals 0.01. So now P x equals 2. What does it mean x equals 2? It means that we got we find the wafer in the second trial. It means that first trial the wafer is okay. Okay, so large particle doesn't there's no large particle contamination in the first wafer. So then probably gonna be 0.99 times 0.01. Okay, so because the each trial is independent, so we just multiply them, right? Okay, so now doing this, then we may get the formula for that probability. Probability x equals x. You see, I told you capital letter X represents just a random variable, okay, and then lowercase x represents specific value of random variable. So now then lowercase x could be like 1, 2, 3, 4, 5, 6, right? So now then let's say the x means that 1 through the 1 minus x minus 1 up to x minus 1 wafers don't have large particle contaminations. And then x, the trier, we got the what wafer containing large particle contamination. Then what's the probability that we're gonna get that kind of situation? I mean the that the orange, then this is gonna be 0.9 to the x minus 1 times 0.001. So that's the formula of that probability. That we can consider this one as what? The definition of probability mass function of that experiment. Okay. So now then you may have to show that, okay, is this, then we have to show that what? Is that really the satisfy all three condition of probability mass function? Yes. Okay, why? Because the this function is greater or equal to 0 for any choice of the what? The value of random variable, actually 1, 2, 3, I mean actually natural number, right? So this function domain must be what? Natural number. Okay, and then the range is gonna be what? The real number, but not but what? 0 to 1. Okay, so it should be 0 to 1. And then a sum of this one, since the give me a second. Yeah, just let me explain in the sketch papers. So we deal with this one, right? So I want to show that that function f of x is a probability mass function. Then we have to check three conditions. So first one is what? F of x is greater than or equal to 0 for any x. X is 1, 2, 3, 4, 5 natural number. Okay. So yes, why? Because 0.98 to the x minus 1 is greater than or equal to 0 for any x, right? Okay. And then it makes sense, right? Because, you know, what's the graph of this? This one, right? Okay. So since the graph never across the x-axis, below the x-axis, right? So 0.98 to the x minus 1 must be what? Positive, right? Okay. So now, oh, it should be, give me a second. It must be like this, sorry. not this one. Okay, this one, because 0.9 is less than 1. Okay, so this one, even though this, so the graph never across the x-axis. Okay, and the 0.01 is a positive. So positive times positive what? So still positive, right? Positive times positive is positive. Okay, the second one, the sigma, and then sigma, and then what? Can you see this? Oh, okay. Yep, the sigma of the f of x. Okay, and then let me use I. Okay, he said let me use I. You don't have to use I. Okay, so I. Okay, that's enough. And then x goes 1 through the what? Infinity, right? Okay, that is equal to 1. We have to show this. Okay. Yeah, let me prove this. It's not a big deal. Because see, this is what? Geometric series, right? Okay, so this is sigma x equals 1 through the infinity, and then f of x is equal to what? Sigma x equals 1 through the infinity, and then 0.01. Yeah, okay, so let's say 0.01. Let me write down 0.01 first, and then 0.99 to the x minus 1, is it? Okay, remember that in a geometric series, sigma, and then a times r to the, r to the k minus 1, and then k goes 1 through the infinity is equal to what? Remember that? A over 1 minus r, right? If absolute r is less than 1. Okay, so that is equal to what? 0.01 over 1 minus 0.99. Oops, it's not. Okay, so that is equal to 0.01 over 0.01. This is 1. Okay. Next one, that last one. The f of x is equal to probability that x equals x. Yeah, so that's trivial. So we define the f of x from here. From here. Okay. So that's a trivial, right? So we just we don't have to prove this. So that's why we can say that, oh, that function is a probability mass function. Okay, this is a probability mass function. So that's the 3.1. So give me a second. Okay, give me a second. Yeah, that's yeah. So the next time I'm going to cover 3.2 cumulative distribution functions. So let me stop here.